Recording in progress.
When we talk about the heat transfer, there are three main ways the heat transfer: conduction, convection, and radiation. Conduction happens in solid, convection in fluid, liquid, or air, and radiation when there is no medium present. So the heat can still transform in the form of the radiation as from sun to earth. So we are going to focus on the conduction. Now, when we talk about the conduction to a flat plate, it depends on certain factors. Now, these factors are, let me write this down. The area of the plate, temperature difference, temperature difference between the phases, time taken for the heat transfer, thickness of the material, thickness of material to which the heat is passing, and type of material. Now let's see if I draw, let's say this is a plate. So heat transfer area is this one. So let's call this one as heat transfer area. We call this one, let's say, is A. Direction of transfer is this. This is direction of heat transfer, HT, heat transfer. Okay. Let's say if I just take a part of the plate and I call that part as a delta T, and I just take that section along the x-axis and I call this section as delta x. So this is delta x, and this section here is delta T. So we assume like we will just draw a formula, and we use that formula later on. If you increase the difference between this and this, temperature difference between that and that, the heat transfer will be faster. If you decrease the temperature difference between that surface and that surface, the heat transfer will be slower. If you increase the thickness, the heat transfer will depend on what material you're using actually. It will be slower. If the thickness is more, the heat transfer will be slow. If the thickness is less, the heat transfer will be quicker. It also depends what material you got. Do you have a very good conductor or you have a very good insulator with a good U value, bad U value? We'll talk about the U values later. Okay. Now let's say if we got the Q is, let's say, is the heat transfer. That is directly proportional to the area, and it's also proportional to delta T over delta X. Now delta T, this is kind of integration. We can use the integration formula. Now if I get rid of this proportionality sign, I can make it like this, but I have to introduce a constant. I can put the constant. Now this constant depends on the material. We can call this constant as anything, so I'm going to call this constant as K. I just introduce a constant K. Now because the heat is flowing from a hot body to a cold body, the hot body is losing the heat energy and the cold body is gaining the heat energy. So we need to put a negative sign here. Now the K is a constant proportionality, depends on the material. Then we got the Newton's law of heat transfer. The Newton laws of heat transfer is, let's write it down. Q equals minus Ka, so exactly same, minus Ka over X. Instead of delta X, I just put X. But here I put a T2 minus a T1. T2 minus T1, these are, K is the constant, A is the area, X is the thickness, and these T's are the change in temperature, temperature 2 and temperature 1. So T's are the temperature. If we talk about the rate of transfer, this is a heat transfer. If I want to do the rate of heat transfer, obviously I need to do per second. Yeah. And when I do that one, there will be, okay, units of this one are joules. But if I put a dot on top, that will mean joules per second, which is, well, we leave it joules per second, much easier. Or if you want, you can call it like as watts. Okay, the next one. Now, let me just put the notation here, all the notations. K is a constant of thermal conductivity, that's K. K is the area of transfer. We use meters here. Inlet phase temperature. We do that in centigrade. Exit phase temperature, that's in centigrade, and we got the unit for this one is watt per meter Kelvin. Just pause that one. And then there is, okay, now we got different K values for different materials, different K values. For air, the way at still air at 15 degrees, that's the K value. Aluminium 206, brass 1 and 4. Break, different types of breaks. So let's say it's the most common break used. It's 0.06. Concrete. Right. Copper 380. Cork.
We assume we don't have to memorize these.
No, that's why I'm writing down. Okay, the glass is that if I got the glass fiber, the value is 0.04. So I just put that in the middle. Okay. So we got magnesium. Magnesia is 0.06. Plastic is 0.04. Okay, these are some common values. The other are steel is, did I write steel? No, I didn't write steel. Steel is 60. Let me write that one here. Steel is 60. Wood is 0.15, and paper, wallboard, or paper, that is 0.076. Yeah. So these are some values. Now, why these values are important? Because if you want to find out the conduction to a composite material or any two material, we can find out how the heat is going to transfer. Let me just. Let's say we got a composite wall. In composite wall, let's say it's made of like 3 different materials, 1, 2, 3 different materials. The 3 different materials has 3 different thickness. So let's say that's maybe a brick, wood, or maybe a foam. 3 different materials have 3 different thicknesses, and that's how the wall is made. So now the temperature here is T1. As it moves, as the heat is transferred, what will actually happen is there will be a decrease in the temperature, hence that T2 is down, the T1. Yeah. Now the thickness of the first wall is X1, thickness of that one is X2, X3. They're all different thickness. Now in material 2, and they have a constant. So the constant here is K1, the constant here is K2, and the constant here is K3. In material 2, the temperature, the starting temperature is T2 on the hot side, and then on this side, it's going to be T3. And then from here, this becomes the inlet, and that becomes the exit. So T3, the temperature on this side of the wall is T3 for the material 3, and T4 on here. Now we got the equation. We use exactly the same equation. Q equals to K1 A T1 minus T2 over X1. And it's also, this is for the first part. For this part, this is going to the heat transfer. For the second part, this is going to the heat transfer. For the third part, this is going to the heat transfer from here to here. So I can call it like Q1, and I can call the other as Q2, and I can also call that one as Q3. So I can call that one Q1, Q2, Q3. If I want to add these heats, that would be the total heat that's transferred from the point T1 to the point T4. Okay, so what we're going to do is we are going to make T1 minus T2 subject in the first one, T2 minus T3 subject in the second one, and T3 minus T4 subject in the other one. So let's have a look. So if I take that equation and I want T1 minus T2 as a subject, that will be Qx1 over K1A. If I do that one as a subject, that becomes a T2 minus T3. That's going to be Qx2 over K2A. Now, if I do T3 minus T4, that's going to be the same thing. Okay. So we just got that bit. Now, if I want just to find out the K, if I just want to find out the K, or if I want to find out T1 minus T, if I add all of these together, there are two ways of doing it. I do the quickest way. If I add all these sides together, this one becomes T1 minus T2 plus T2 minus T3 plus T3 minus T4. So that side will become a T1 minus T2 plus T2 minus T3 plus T3 minus T4. Now you see this cancel out, this cancel out. So you only got T1 minus T4. Yeah. And on this side, if I have a look, I have the Q and the A common. So that becomes a Qx1 over this thing, Qx2 over this thing. So I can take the Q and A common. And I'm left with, I'm adding them. X1 over A1, but they are same because the area is the same. X2 and X3. So from here, oh yes, not A1 because A is inside. Thank you for, yes, so that's K1 because I've taken the, yes. Okay, thank you for that.
Now we just go to correction call.
Yes, so we got T1. Now the equation can also be written in the simplified fashion as well. Now, if I want just a Q, the total heat transfer, I can make the Q the subject. I'm making this Q the subject. This comes here. So that will be A times a T1 minus a T4. So we don't consider T2, T3, just the first inlet and final exit. This thing, yeah, I need to put here. So this thing here is multiplying. On the other side, it's going to divide. It's going to be like this. X1, X2, X3, K1, K2, K3. So this is the heat transfer from point 1 to point 3, 2.4, yeah, in a composite wall. If you are given the K's value and the thickness value and the initial and final temperature and the area, you can find out the value of the K. Now, there's another formula in terms of summation. You can write this one out, but to be honest, it's not necessary. I'm still going to write it down. I need to move this thing down. Okay, so to do that one, the top as it is. This one you can write in this form, the summation X over K. Now, The top one, I put T1 minus T4. This can also be written as T1 minus T n plus 1. How many walls are there? See, there are 3 walls. So that is 4 there. So you can do that one. For here, you can write down it starts from initial is 1 and ending at n. Yeah, this is the notation we have to use. Initial value, write it here. I is 1, like I start from 1, or just put 1 and ends at n. Yeah, because there can be 20 different walls, different thickness, different materials put together with the same thing. Okay. Now we are going to do one numerical question. Let me stop the recording. Okay, now let's say we got a question where we need to find out the heat transfer to our system where we got 2 components joined together. One is brick and one is one is concrete brick and the other is, let's say, cement. So brick and concrete, let's say we got 2 different things now. They both have different thickness. So concrete is 50 millimeter thick. And we have different coefficient. For the K for the brick is 0.69, which is 250 millimeter, and the concrete is 50 millimeter, and that has a coefficient of 0.9. We need to find out the heat loss per hour. Now remember, this one is the heat formula for the heat loss per second. So we need per hour. Whatever answer we get, we need to multiply it by 3,600. Now, this is the brick material. We got the value of the X1, 250 millimeter. K2 is 50 millimeter. No, not K2. X2 is 50. K2 value is given. And then we also need to find out the interface temperature as well. The interface temperature is that temperature here. What's the temperature here as well? So first we use that formula. So T1 minus, that's going to be T3 divided by X1 over K1 plus X2 over K2. Now we need to find the area first. We can find the area from here. Yeah, so I got the area as 50 meters square. We have the value for the T1. T1 is here. We have the value for the T3. No. If the brick face is and the concrete face, yeah, so the concrete face here is that T3. So that is given. So you have the T1, we have the T3. We have the X1. Okay, with X1, make sure you convert this one into SI units. And just put that one back. So A is 50. And you got 30 minus 5. So X1 is 30. No, not 30. X1 is 0.25. And K1, where's the value of the K1? K1 is a brick, 0.69. Plus X2 is 50. Divide that by 1,000. And 0.93. So if you put that in calculator, you will get an answer. whatever answer you got, just make sure you just multiply that by 3,600. And we got an answer for this one. Oh, sorry, let me just move it down. Yep. There you go. For that part, 3,000.
That's what math was.
And 4. Oh, it's and then
multiply it.
yeah, okay, thank you. So let's say 3,004 times that. Yeah, 10 joules are quite small. Yes.
10.8 times 10 to the 6.
How many?
10.8 times 10 to the 6.
Yeah, that's joules. Okay. Yeah, that's fine. So this is per hour, heat loss per hour. Now we've done the first thing. Now the other thing it's asking us to do is find the interface temperature. So this is that thing done. Now we need to find out the interface temperature. Okay, now find the interface temperature. The interface temperature, we got the temperature T1. Now I need to find the temperature T2 between the two interfaces, between the brick, and I need to find the temperature between the brick and the concrete. So then I can use the formula. Area remains the same, everything remains the same. The T1 is there, but then the T2 is the one we are going to find out. Okay, now let's have a look. If we are considering the brick wall, so just for the brick wall, we find the Q for the brick wall. Q, let me write down one. So just for the brick wall, let's find the Q for the brick wall. It's going to be K1A T1 minus T2 divided by X1. It was X1 over K1, but K1 I just put all the way up. So for brick wall, let's put that one. Find the T2 because T1 is given 30, so we need to find the T2. T2 is the missing, T3 is there. Okay. So let's find the T. Okay, so that will be Q X1 over K1 A1, and then that will be okay equals T1 minus T2. Let's do that. And I'm trying to find the T2. So I'll move the T2 here and that thing here. So T2 will equal to T1 minus Q X1 K1 A1. Now once you got that bit, just put the value. So that's an equal sign. Yeah. Now put the value. So T2 equals T1 is 30 degrees minus, okay. Now the Q1, for the Q1, this is the heat we are going to use 3,000 for per second. So we're going to use that heat. So 3,000 4 minus, no minus, X1. X1 is, yeah, so 0.25. Yeah, K1 is from there, 0.69, and the area is the same, 50. So if you put that in calculator, you will have a value of the T2. Okay, so I got the T2 value. Now, I can use the same formula just to want to say like, okay, I could have used the same one from here to here as well, where I can find out the T2 minus T2, T3. It will give me the same answer. So I can use that one. If I want to use a concrete, I can have Q equals to the K2A, that would be X2, and that would be T2 minus T3. So I can use the same formula to do that one. It will still give me the same answer. And that will give you the T2 is a missing bit. If I do that one, you will still get the same that value. Yeah. So it doesn't affect anything. Okay. Let me just pause this one. Okay. Conduction through thin pipe. Now, how do we know it's a thin pipe or a thick pipe? We talk about that one later. Let's say I do a very thick pipe. So this is the thick pipe. In the thick pipe, there is quite a bit of thickness here. If I measure the area from all the way from here to here, let's say I find the area of that one, and then I find the area of this one, they will both have different areas, isn't it? Yeah, they both have different areas. Now, let's have a look at the thin wall. Let's say I got that bit, and this is the thin wall. Okay, now if I measure the area of the outer one, the blue one, and if I measure the area of this one, they are kind of same. So we make an assumption, well, not assumption, reality is the internal surface area is kind of nearly equal to the external surface area. So we assume they are 100% same. They're not, but we make an assumption that they are 100% same, because then we don't have to worry about finding the thickness and so on. Okay. So if the heat is being transferred from here, it's the same as the heat transfer from the other way. So this is the important assumption. Now the formula. If we got a cylinder of radius r, or a pipe of radius r with a length L, we don't worry about the internal radius or the external radius because we assume they are kind of same. And let's say the thickness, let's say the thickness is X. Okay. If I want to find the length of the cylinder, the length of the cylinder will be given as 2 pi RL. Yeah, not the area, sorry, the area of the cylinder is going to give you, the surface area is going to give you 2 pi RL. That's the formula for the surface area of the cylinder. Yeah, just the outer one, not the top two bits. Yeah. Okay. Now, if I want to find out the Q, the heat transfer per second, I got the KA T2, T1 minus T2, exactly same formula. over x, which can be simplified to k is a k, a is 2 pi rl over x, T1 minus T2. Where I got this from? Area of the cylinder. Now, if I, or a pipe, when I draw the cylinder or a pipe, the radius of this thing is an r, and the length is l. Imagine you got CDs stacked on top of each other. Let's say you got DVDs or CDs stacked on top of each other. I want to find the circumference of one CD. The circumference of one CD is 2 pi r if the radius of that CD or DVD is that one. But now, how many CDs I got? All the way up till here. So multiply by L. This will give me the surface area of that one, because I can break it down into different surface areas. And you can do 2 pi RL, yeah? So that will be your area, surface area. We don't consider the surface area, the top one and the bottom one. Surface area of that. So done. This is the heat transfer per second. We need the X. We also need, which is the thickness of the cylindrical wall. We also need, what are we using? Copper pipes, steel pipes, different pipes. We need to use that one as well. So now K value, now T1, T2 in here, if are the surface temperature of the inside and the outside, yeah? So we can find that one. Now, what if we got a thick cylinder? With thick cylinder, it's going to be a little bit different, because obviously then that's not same. So let's do the thick cylinder. Just pause this one. Okay, let's assume there's a cylinder. Now the cylinder has inside radius of R1, that radius is R1, the outer radius is R2. The thickness of the cylinder is, you can subtract the R2 minus the R1, that will give you thickness of the cylinder or a pipe. The length of the pipe, let's imagine it's an L. We also assume that heat flows from the inside to the outside. So we assume there's a hot water or hot thing flowing into the pipe. So heat flow is from inside to outside. Okay. And the amount of the heat that flows is Q. Now, if the if the radius is R, the outer radius, I can take a tiny portion and I can call this one a delta R, change in R. I can use that one. Now, if so what does that mean if it's inside to outside? It means that T1 is greater than T2. Now, if I want to use the same formula, the Q1, I got Q equals minus K times the area, and then delta T over delta R. Now, instead of area, I can put the 2 pi RL. Delta T. You can put the dt over dr, which is same as delta T over delta R, like as in differentiation. You can use that one. Okay. Now, delta T over delta R, that is going to be a negative. Because drop in temperature, delta T over delta R is going to be change in temperature over the radius. That's because the temperature is dropping, not increasing. Okay, I can rewrite this equation again. I can write it like that. Now remember, this delta T is same as you might see different notation. They are exactly same. These are big delta, medium delta, very small delta. So they are same. I use this one because it's much easier to write. Okay. Now, so what I need to do is I can integrate that one. I can just integrate. Now K is constant, 2 is constant, pi is constant, L is constant. The only thing that's changing from the middle to the end is the R is changing. Okay, so let's integrate that one. And the other thing that's changing is the T is changing as well. So I'm just going to integrate and we see what happened. TR or DR. Okay, I'm just going to rearrange the equation. So I move the Q on this side. I put everything on this side. So minus Q over, I'm just putting everything on this side. K 2 pi RL. And that thing becomes a delta R. That thing goes on the top. So now I'm just changing that delta R. Actually, let's write it down here. And the delta T remains on the other side. Yeah. Okay. Now I'm just going to integrate this one. Yes, so on one side, I'm going to integrate with respect to T, other side, I'm going to integrate with respect to that one. So I'm just going to write this one again. Instead of this one, I'm going to put the dt. Okay, this R is not constant, so I'm just going to put that one here, R. And the delta R, instead of delta R, I'm going to call it dr. And then I integrate. For the integration, I add this sign. Now this is the constant. The K is constant, 2 is constant, pi is constant, L is constant. So this one, I can come out of the integration and I can just put the integration here. Now, the radius starts from the R1, which is here, and that one, R2. It goes all the way to R2. That's the limit. Temperature starts from the T1 and it goes all the way to T2. So I just put the limits there as well because I'm just assuming only that pi. Now, when you integrate, let me just drop this bit. When you integrate that thing, the answer will be just a T. So you will have just a T as an answer here. Now this one, minus Q, K, I put 2 pi KL, just rearrange that one. So obviously there are limits. It's from T1 to T2. So T1 and T equals to 2. I can open the limits in a minute. And when you integrate that bit, 1 over R, the integration of 1 over R is ln of R. Yeah. Okay. Now, and obviously there's a limit as well. Limit is from R1 all the way to R2. Now let's do that one. It's the upper limit. The way we open it, upper limit minus the lower limit. So you do T2 minus T1. You put first to put that thing minus then the lower limit. And this one is minus Q 2 pi KL. And that one same. It will be ln R2 minus ln R1. There's another way of writing it down. T2 minus T1 equals minus Q over 2 pi KL. And this thing can be written as ln of R2 over R1. When the logs are subtracting, you can write in the form of the division. So this is a formula to find the heat loss. You can rearrange it to make Q the subject. You can make Q the subject if you want to, and you can find the heat loss. Let me just make the Q the subject. So if I'm making Q the subject, Q equals to 2 pi KL T2 minus T1. Okay, I'm going to write it, but I will rub it in a minute. Don't write the T2 minus T1 in a minute. And ln, you just put the ln from here, and you need to put that on the other side. So that will be divided by ln R2 over R1. Now remember, there's a negative here. You see there's a negative here. I can pick up the negative, put it here, or simply I can change that to 1 and that to 2. Yeah, so that's the easy way, rather you moving that negative. So you change that one. So this negative this is the final formula. If I give you the K, if I give you the length, if I give you the internal temperature, external temperature, and the internal and external radius, you can find out the heat transfer per second. There's a Q dot on top, which means a per second. Okay. Okay, let's say we got a question. Steam pipe 75 millimeter, external diameter is given 80 meter long. It conveys 1,000 kilogram of steam per hour at the pressure 2 mega Newton per meter square. Steam enters the pipe with a dryness factor of 0.98 and it leaves with a dryness factor of 0.96. The K is given, the coefficient of is given 0.08. Assume the temperature drop across the steam pipe is none. Find the minimum thickness. Take temperature of the outer surface as that one. Now, first thing we need to do is we need to look at the steam tables. At 2 mega Newton per meter square, what's the enthalpy of the evaporation? We will get this value, 188.6 kilojoules per kilogram. Enthalpy values depends on the pressure. You can evaporate something on here and at 100-degree water. But if you take it to space or low pressure, maybe the water will boil even at minus 10 degrees centigrade because there is no pressure. The water remains in the water state because there is atmospheric pressure pushing the molecules down. So make sure the molecules are not, doesn't leave the surface. Okay, so we have that one. So pressure plays an important part. Okay, so we got that bit. Now after that, we got the dryness factor. So dryness factor is given. So we need to find out the heat loss. Heat loss per kilogram of steam when passing through pipe. Yeah. Okay. Now this heat depends on the dryness factor as well. So it's going to be 0.98 minus 0.96, difference between the dryness factor, multiplied by the HFG value. Now this value is 18.6 kilo. Remember that one kilo. So we'll get that one answer in kilos straight away. So we don't have to convert that one. Okay. So if you got the answer, please.
That 0.6.
Yes, 0.6. 30. Okay, now this was in kilojoules, so you do kilojoules, and this is per kilogram, so that's it. So kilojoules per kilogram, it's 1 kilogram, it's like that. Now you do 1,000 kilograms of the steam per hour. So we are doing 1,000 kilograms of steam per hour. Now, if you're doing 1,000 kilograms of steam per hour, obviously this is per kilogram. 1,000 kilogram, we need to multiply that one. Okay. Before we do that one, let's have a look at the formula. We got the Q, heat loss per second. Okay, heat loss per second is going to be Q dot 1,000 divided by this thing times 37.77. 37.77 kilojoules on the top. This is per hour. Yeah, this is a per hour because it takes per hour. This is per hour. Now we need per second. So divide that by this thing. This time this, convert kilojoules into joules. So if you put that one, this is joules per second. You will get joules per second. 10.5? 10.5 kilo? Is it kilo?
No. It's, yeah, we kilo, kilo, yeah.
Okay, so 10.5. Okay, we got that bit. Okay. Now the next bit is for a thickness. We need to find the thickness. Now we need to use that formula. So 2 pi KL T1 minus T2 over ln R2 over R1. Okay. Make ln R2 R1 the subject because that's what we need to find out. So this is thick pipe or thick cylinder. Okay. So we got that bit. Now, rearrange the formula. Let me do that one here. Rearrange the formula. This goes here and this comes here. So the Q is here and this side is going to be ln R2 over R1. Now put in the values and we get the answer. Q is 2, pi is pi, 0.008, no, 0.08, 0.08, and L is 80. Okay. Now what is T1, T2? Okay. Now I just put that one in a minute, and the Q is 10.5 kilo. Okay. Now T1 and T2. T2 is that value. So the T2 is, okay, T1 from table. T1 value is the saturation value. Saturation temperature at 2 meganewton per meter square, which will be from the table, and that is 212.4 degrees centigrade. So that's your T2, and you put the value here. Did I T1 minus T2? Oh, it should be other. No, that should be T1. Oh yeah, that's right. It's T1. Sorry, you're right. 202.4 minus 27. So if you put that one, you will have ln R2 over R1. You will have a value. I got 0.71. Okay. then you can take the anti-log. Anti-log or anti-ln. So here you got R2 over R1, and when you take that one, I will show you how to do it. Okay, so we got the R2 divided by the R1 is 2.03. If you draw a circle here and the other one, the external diameter is 75 millimeter is external. So what is that from here to here? What's that one? It's 75 divided by 2, isn't it? The total diameter is 75. So the radius is going to be 75 divided by 2. That's the outer radius. Now, I don't have, do I have the thickness? I don't have the thickness. This is what we're trying to find out. Now, I got the R2 over R1 is 2.02, 2.03. So I can use that one. And I can rearrange that thing to find the R2. So I got R2 is 2.023 R1. I got that there.
Yeah, which is R1 and R2?
Say again?
Which is R1 and R2?
Which one is R1?
R2.
Okay. No, R2 is bigger.
R2 is the outer radius.
Yes, R2 is bigger because you can see 2.03.
Oh, right.
Yeah, you can see 2. So it's a bigger one. R2 is the bigger one. Okay. Okay, now if you put in the values, I said if it's bigger, then if I put the R1, there is the R1.
We don't know the R1.
Yeah, but we know the R2. But
You can work it out.
yes, but I'm thinking, did I put the formula right? Is the R2 or R1, not the other way around? Did I put that one? Okay, can you guys check this formula? Did I put this one right, or is R1 or R2? Okay. Yes, so R1 is R2 divided by 2.03. R2 is here, 75, but you need to actually convert that one. And that will give you the value of the R1. Just put that one, and then for the thickness, the outer minus the inner radius, and that will give you the thickness. What's the answer we got?
19.06.
19.
That's 106.
And 19 millimeters. Yeah, that's sensible. 19 millimeters.